The next thing that I want to talk about is controller networks. We've already established that we do have them and why we have them. But what types of networks do we use for our BeMS system? Well, in order to understand just a little bit about networks, you need to look at the difference between communications media and protocols. I'll say this is a 1-hour course. You don't need to understand this, but you do need to understand the difference between the two. The communications medium is the physical wiring which is used to connect the devices together. And in BeMS, we have two very, very common types of interconnections between our devices. We use Ethernet, which is the same kind of wiring that you use for IT infrastructure, Cat5, or more recently it'd be Cat5e or Cat6 cables that we use for Ethernet, and two-wire RS485. Now, the two-wire RS485 is typically used for lower powered, lower bandwidth devices, whereas Ethernet is used to connect your main plant controllers together. There are other media types. You may come across Longworks FT10. It's quite unlikely. It seems to have gone by the by, but there are plenty out there. Mornitz passing as a network, it worked really well. It was incredibly robust, but it came with its own set of problems. So the two emerging technologies that we've seen, or the two predominant technologies, I should say, rather than emerging, are using Ethernet and two-wire RS485. Something else about RS485 and Ethernet, which they don't share with Longworks. Longworks was designed for building automation. Ethernet and RS485 have very broad applications outside of building automation, so they are supported elsewhere. And that means that you've obviously got a lot more people developing it, and you've got a lot lower cost for your devices because a lot more people are using it. So those are the communications mediums. That's the physical media that we use to send our electrical signals over. A protocol is slightly different. Protocol is a language or a set of common rules used to exchange data between devices. Now, if I have a telephone and my friend in Paris also has a telephone, we have everything we need to communicate with each other. However, if he is speaking in French and I am speaking in English, then we obviously can't understand each other because we don't have a common set of language rules. Obviously, he would need to speak English because that's just how this works. But we need to, everyone needs to be speaking the same language in order for that communications media to work. So the protocol is the language. Protocols are either proprietary or they are based on open standards. The thinking has traditionally always been towards proprietary protocols, and the reason that manufacturers wanted to do this was it got vendor tie-in. If you had your own protocol, you would sell your BeMS to a client, they would put it in the building, and you couldn't use anyone else's controller in there. But of course, the opposite argument to that is that, well, the building next door has got your rival's equipment in it, and now we can't put any of your equipment in it. So gradually, people came around to the idea of using open protocols. A lot of pressure was put, client pressure was put onto manufacturers to make this transition, because obviously it benefits the end users most. Of the open protocols, the two most common that we find at the moment, things are changing because of IoT, but right now we are looking at BACnet, which is the Building Automation Control Network, and Modbus. Modbus has been around for a very long time. Modbus was invented at the tail end of the 1970s by a German company, I believe they were, Modicon anyway. Because technology was quite limited in the 1970s, Modbus is extremely difficult to work with. It's all about sending ones and zeros, and they have to be sent in a particular way. And as I said, if you've got any BeMS engineers listening to this who've worked with Modbus, they will know it's a real pain to work with it. Modbus is very lightweight, it's extremely robust, and it's been around for a very long time. And we don't expect it to go anywhere. What's actually happened with Modbus is that it was originally designed for very large scale process control plant. We now see it implemented on the smallest of field devices. So if you buy a sensor, then it will typically be able to communicate using the Modbus protocol if it's a smart sensor. With Modbus, though, you need to know what every point in that system is doing in order to communicate effectively. There's also other problems with Modbus. One of the problems is that there is nothing in the standard to say whether you need to send the high bit information or the low bit information first, so it can make it quite difficult to work with. The next one that we're going to look at is BACnet. Now, BACnet was developed by ASHRAE, which is the American Society for Heating, Refrigeration and Air Conditioning Engineers over in America. The difference between BACnet and Modbus is that, or the first difference between BACnet and Modbus is that BACnet was designed specifically for building automation control. That was what it was there to do at the outset. And so the people who sat down thought, okay, what are the problems? What do we need to be able to do? So BACnet has been developed around that thought process. There are two particular features of BACnet, the who is and I am commands, which set it apart from so many other protocols. The who is I am commands mean that you can send out a broadcast message to a network asking who is, what other BACnet devices are here, and you can receive an I am response from those other devices on the network. From an engineering point of view, if you walk onto a site and you can plug in and find everything, that is brilliant. But obviously, as we've started to migrate our networks onto customers' IT infrastructure, this has led to issues with security implications. The BACnet standard constantly evolves. There are new iterations coming out all the time, and they're trying to address the security concerns with it. But there is a kind of adversarial element to BACnet where engineers like me love it. IT engineers, because of the security side of it, are not quite so keen on it. So you have to implement security. But it is an open protocol. Anybody can implement BACnet on their system. You have to meet a certain certain criteria set out by ASHRAE in order for your device to be BACnet compliant. There is a myth that if it doesn't bear the BTL mark, which is the BACnet Testing Laboratory mark, that it is not a true BACnet device. That is actually not true. BTL assures that it meets the BACnet standard, but you do not have to bear the BTL mark in order to be able to make and sell a BACnet device. You have to be compliant with the standard, but you do not have to bear the BTL mark in order to show that compliance. You can do your own testing. The last one to just have a quick look at is MQTT, which I'm fair convinced, having been at smart buildings for the last couple of years, is going to emerge as a very strong contender for the Internet of Things revolution, which we seem to be at the dawn of. MQTT stands for Message Queuing, Transport and Telemetry, and it uses what is called a publish-subscribe model. You have a broker which sits somewhere in your system. Now, this can be on the internet or within your facility. Devices publish information to the broker, and the broker then disseminates that information out to any device which is subscribed to it. So that's the publish subscribe model. Now, MQTT was not developed for building automation. MQTT is actually the protocol which is used for Facebook Messenger. If you think about how Facebook Messenger works, if you've got a group chat going on, you have a broker which has a topic, which is your chat. You publish a message to that broker, and then anyone else who's subscribed to that, all your friends in that chat, they also receive the message. So MQTT is supported well and truly outside of our industry, and it's certainly, as I say, at the moment, it's emerging as the contender for the protocol of choice for the Internet of Things. In terms of network architecture, notwithstanding MQTT, a very common form of putting our networks together is we have a high-level devices sitting on an Ethernet backbone. So if you think in terms of real controllers, if you've got a Trend system, for example, Trend IQ4 controllers are all equipped with Ethernet ports. So you would connect them together with Ethernet. If you then wanted to communicate with other devices, which were also using the same protocol, so we'll assume we've set this up to work with BACnet, then you need to move from Ethernet onto RS485. So you would have to go through a router. If you're using Trend, then presumably you'd use something like an IQ4NC to do this, provide your routing. If you were using just a non-proprietary BACnet system, you could use any BACnet router to take those BACnet packets onto RS485. RS485 has limitations over Ethernet. The bandwidth that you can use on RS485 is much lower. So on Ethernet, we can communicate at about, for controllers, about 100 megabits per second. On RS485, we're typically running at 19,200 bits per second. So that's it's a lot slower. But that's perfect for connecting smaller devices together. And it's a lot cheaper to run in an RS485 network than it is an Ethernet network, because with RS485, we daisy chain from one device to another rather than having to bring everything back to a switch. If we're moving to a different protocol, then we use a slightly different device, and it can be a bit confusing because routers and gateways will often be in the same enclosures, but a router and a gateway are two different devices. Routers take data packets from one type of physical media, and then they transpose those data packets to a different physical media. In a gateway, we've actually got two different protocols working on our system. So on one side, we might have BACnet, and as is shown in the diagram here, on the other side, we've got LonWorks FT10 network, which uses the LonTalk protocol. So we need a gateway. When we have a gateway, it is an engineered device. BACnet, you have a BACnet address, you send it to a router, it retains a BACnet address and sends it off down the RS485 network. With LonWorks, a LonWorks device does not have a BACnet address, so we have to engineer the gateway to say that when a piece of data arrives for this device, then it needs to be transposed to device X or Y on the LonWorks network. So we have routers and gateways in our system. Again, as I say, this is not an in-depth look at networks. It's just a very brief view of how we might put our networks together. We also see a prolific amount of digital field bus devices these days. Smart sensors. Smart sensors and actuators. You seem to see more sensors than you do actuators. They have got the communications built into the devices themselves. So we don't need to connect these sensors up to a DDC controller to an analog input or an analog or digital input. We can actually daisy chain them together using an RS485 network and get the information out of them that way. Now, this can obviously reduce wiring costs, but it also gives you huge benefits if you require multiple variables. For example, if you have a requirement in a space for carbon dioxide monitoring, relative humidity monitoring, and temperature monitoring, and you can get a single unit with all of those variables or all of those sensors built into it. Doing it the traditional way, you would have to wire 3 cables back, one for each of the sensors that you're working with, and you would have to use 3 analog inputs on your controller. Bear in mind, there is a limited amount of analog inputs, so that might not be desirable. If you use a smart sensor, then all of these variables appear on the network. So you network them all together. You use no analog inputs for your digital bus at all. The signals are also lossless. That means that when you get a signal on a digital bus, it is transmitted as ones and zeros. It's not a varying voltage. So we don't have to concern ourselves with overly long cables. I mean, we still have to pay attention to cable types and cable lengths. But if you have 100 meters of cable to an analog sensor, you will get a voltage drop on it. And if you're measuring 0 to 10 volts DC, you need to account for that. You don't need to do that with smart sensors.